So this is my handout for the beginning of Gauss's law, to just go through all of the examples so that you can do simple and more complicated problems. So we're going to go through, use Gauss's law to calculate the electric field of the following charge distributions. For each charge distribution, include a drawing, include the Gaussian surface and the direction vectors for the normal, or dA, right? That's the normal is the direction of the area vector of the Gaussian surface. So I'm going to start with the drawing. Sorry, so this is a point charge. So let's say that's my point charge, and then my Gaussian surface is just a sphere around the point charge. I need to draw my E field, right, perpendicular, and my dA is in the same direction. I make dA smaller because it's just a unit vector, so it's just telling me that it points in the same direction. So that means that my Gauss's law is E dot dA, right, is equal to Q enclosed over epsilon naught. So my E dot dA, since they point in the same direction, I just get E and dA. And then note that because I can pull E out of the integral because it's a constant all along my Gaussian surface. So E doesn't change, and I know that because I'm not moving away from the charge. I'm at the same radius away from this charge. I'm also going to label the distance from my charge to the Gaussian surface as R. So then I have dA is equal to Q enclosed over epsilon naught. Now the integral of the area of my Gaussian surface, since I know it's a sphere, I picked it as to be a sphere, and I know the area of the surface area of a sphere is 4 pi r squared. So this is the r that I'm using because this is the Gaussian sphere, so 4 pi r squared is equal to Q. Now what is Q enclosed? So Q enclosed is really, from the problem, is just Q. So I can just plug in Q, because that's what's inside my Gaussian sphere. Q over epsilon naught. And so then I have E is equal to Q over 4 pi epsilon naught r squared. And then what about direction? So I need to include direction, and I know E points away. So away here, if I think about the R direction, right? R can point in any direction, but it always points away. So E is pointing in the same direction as R, right? If I drew the radius here, my E should be pointing away. And my drawing isn't great. My my Q should be here in this circle, and then you'd see R and E are parallel to each other. So I'm going to write R hat, so I know it's in the R hat direction. And there we go. So there's my answer. Okay, so let's move on to B. Right, this is an infinite line of charge, and again, I need to draw my line, right? My surface now, I need a volume around it, so I'm going to make like a Coke can, right? And if I think about the field of a line of charge, right, the field points away from this positive line of charge. So if it points away, then on my Gaussian surface, right, my E field is going to be pointing away. So E is going to be pointing away at any point on this Coke can, right? And so this is my E, and this is my dA. So they both point away. Now, well, what about on the ends? Because when I'm thinking about Gauss's law, I have to consider the whole volume, right? So here, this is my dA, because it points away from the surface, but my E field points like this, up. That's my E. Same thing over here. This is my dA, and this is my E. So when I go and do Gauss's law, I'm going to say E dot dA is equal to Q enclosed over epsilon naught. But now thinking about this volume, I really have three pieces. The two ends are two pieces, and then the circular part. So I'm going to say, let's call this 1, 2, and 3. So I'm going to have three pieces, and let's call 2 and 3 the same thing, right? So I'm going to have E dA1, let's call this 1, plus E dA2 plus E dA3. is equal to Q enclosed over epsilon naught. Okay, so 1 and 2, or let's look at 1 first. If I think about 1, I've got my E and my dA. They're both pointing out and away, right, from my line of charge. So I'm going to keep this, right? This should be dot. Oh, I forgot my dots. And these should all be vectors, because I'm going to get rid of the vectors, but I need to consider the dot products first. So this one is E dot dA, so I'm going to have E dA. So that's my this circular area. But what about 2 and 3? Well, if I look at 2 and 3, a dot product is, you get the full, so a dot product is E dA cosine theta. And if I think about the cosine of E and dA, they're pointing perpendicular to each other. So that means I have cosine of 90. And cosine of 90 is equal to 0. So here I'm going to have E dA cosine theta, or cosine of 90. And then there's 2 of them. They're both in the same boat, right? So I have 2 of them. But since this is equal to 0, the whole thing goes to 0. So this term goes away. So I'm just left with this term for the circular part of my cocan. Lots of people forget about the ends, but if you're doing this completely, you need to remember that's why, because E and dA are perpendicular to each other. So EDA for the circular part, now I know E is a constant everywhere on the outside of my cocan, so I can pull E out. And now what is my dA? Well, if I think about this cocan, right, imagine if I were to cut it with scissors, then it would look like a rectangle, so kind of like this. Right? So I've just taken my cocan, cut it. There's no end. Imagine the ends are open, like I've chopped off the 2 ends of my cocan, and I then snip it with scissors, right? And I get this rectangle. And so if we call this our length, right? So this is going to be our length, and this is our width, right? Then I'm going to have my dA is going to be length times width. So L times W is equal to, now let's talk about Q enclosed. So they tell me this charge density lambda, and lambda is equal to the charge, so Q, over the length. And it's the same length here, right? So, so my Q enclosed is this, the charge, right, along a line. So this is a charge density, charge along a line, and usually, like it's infinite, so I can say now my Q is equal to lambda L. So I've got lambda L here over epsilon naught. So I'm just plugging in Q enclosed is just lambda times L. So now I can cancel my L's, and I get E is equal to lambda over epsilon naught. And if I think about my W here, right, this width, right, is really, what is my width equal to? It's equal to, imagine this is a circle, right? So all I'm doing is my width here is really just the circumference of a circle. So I'm going to have 2 pi r. That's this length, so I can plug that in for this W, right? And so in order to, I can divide then by 2 pi r. So I've got 2 pi r. So it's 2 pi epsilon naught r. And now what direction is it in? Well, this is my r, right? So at any point along my, pointing away from my cocan, I'm in the r direction. So I'm going to have the r hat direction, and then E goes this way, right? That's just setting it as a vector. Okay, next. So next I have a, see if I can pause this for a second. Sorry, I had to get something out of the oven. So an infinite plane of charge. So on this one, my drawing is going to be like a sheet, right? And it extends forever. And so what I want to do is I need to have charge going through a surface, kind of like we had over here. So I'm going to use the Coke can again, but this time I'm going to have it go through, like this imaginary surface, right, is looking like that, right? So this is the part of the sheet, right, that's inside my volume. So now I need to think about here. So my electric field points away from charge, right? So this is a positively charged sheet, so my E field is going to point away. So that means I'm going to have an E field pointing away. So my E here is going to be pointing this way, and my dA is going to be pointing this way. So this is dA, this is E. Same thing here. My sheet is positive, so it's going to be pointing away on the back side. So my E is going to be pointing this way, and my dA is going to be pointing that way too. What about here? My dA on this round part of my Coke can points this way. So what do you think is going to happen on this part of my Coke can, right? It's going to go away. So I'm going to have three parts, this side and this side. So I'm going to have, let's call it E left dA plus E right dA. So this is the end of the can for the left. This is the end of the can for the right. And then this is my cylinder part, plus E, we'll call it cylinder dA. Right? Dot products on all of these. Integrals, and then is equal to Q enclosed over epsilon naught. So the left and the right, I keep them because my E and my dA point in the same direction, but my cylinder part, this part's going to go away, right? Because they're perpendicular to each other. My dA points away, but my E points this way. So I'm going to have E dA cosine theta, but theta, just like up here, is 90, so this is going to go away. So this goes to 0. So now I have two of these, so I'm going to have 2, and then we'll just say E is the same here as it is there. dA equals Q enclosed over epsilon naught. Okay, so now I'm just going to say, this is kind of, I could say my area is pi r squared because that's the area of a circle, but I'm just going to leave it as A, and you'll see why in a sec because it just makes it easier. Q enclosed. So Q enclosed, they tell me the surface charge density. So I know surface charge density is Q over area. Okay, so if I want to then plug that in, right, I'm going to say Q is equal to sigma times area. So I'm going to have sigma times area, right? I'm plugging in for Q enclosed. This area here, right, is the same as this area here. So these two areas are the same. That's what I'm enclosing over epsilon naught. So I can cancel out the A's, right? And this gives me E is equal to sigma. Let's just fix that. E, gotta slow down a little bit, and so I don't get these weird lines, over 2 epsilon naught. And it's pointing away, right? So I could say, if I looked on the right side, so if I consider just the right side, I would call that the x hat direction. Right, so I know it's pointing in the x direction the way I've drawn my picture here. So that's a couple of the examples, and let's go on to the next one. So spherical ball of charge with a charge density rho. So this is like what we did yesterday. I'll just go through it quick. So this is my spherical ball of charge, right? My Gaussian surface. All right, my E is going to point. So my R goes out to here, right? My ball of charge, let's say that has an area or a radius of A, and then my electric field, right, is going to be pointing this way. So that's my E. My dA is pointing the same direction, right? So I've got E dot dA is equal to Q enclosed over epsilon naught. So remember, my E is a constant at all points along the sphere, along the Gaussian sphere. So I'm going to pull that out. And now what is the integral of dA for my sphere? I know that's going to be 4 pi r squared. right? And that's equal to, okay, Q enclosed. So I know that rho is equal to Q over the volume, right? So the volume of this, so this is going to be 4/3 pi r cubed. So pi, not r cubed, 4/3 pi a cubed, right? Because it's not r, because my charge only goes out to a. So if I were inside, I would use little r, but since I'm outside, right, the maximum, I don't have any more charge, so I don't have charge out to r. Right, so I'm going to plug this in. So Q here is equal to rho times 4/3 pi a cubed over epsilon naught. So E is equal to, cancel out my 4 pi here. So I'm going to have rho a cubed over 3 epsilon naught r squared. And this is again in the r hat direction. And what about inside? So now if I go inside, right, I'm doing this, and my Gaussian surface is inside, my E points this way, my A points this way, dA points this way, this is my R, this is my A. So now I'm going to have E dotted with dA is equal to Q enclosed over epsilon naught. So my E is the same everywhere on the sphere. I still have 4 pi r squared. I go out to the r of the little sphere here. And now Q, so I've got rho is equal to Q over 4/3 pi. Now it's going to be r cubed, right? Because I'm only going out to this far. I don't get all of the charge that I would get for going out to A. So I'm going to have, I'm plugging in Q is equal to rho times 4/3 pi r squared. Pi r cubed, sorry, over epsilon naught. And I can cancel out my 4 pi. And I can cancel out this r squared and two of the squareds here. So I'm still left with r. So I get E is equal to rho over 3 epsilon naught r. Right? And then that's my magnitude, and now it's in the r hat direction. It's pointing away because the charge, we're assuming it's in the positive r direction. So that's it. Those are the main simple Gauss's law, and then you can apply those to any other Gauss's law problem as it becomes more